Let's talk about cardiac output. Now, before we talk about cardiac output, let's define it. So, it's defined as the amount of blood pumped by the left ventricle per unit time. So, the volume of blood pumped by the left ventricle per unit time. Okay, how do we calculate cardiac output and what does it mean and what affects it? And yeah, so you calculate cardiac output by the equation stroke volume times heart rate. So cardiac output equals stroke volume times heart rate. What's stroke volume? Stroke volume is the amount of blood pumped by the left ventricle per one beat. You get stroke volume, so the amount of volume per stroke. Kind of makes sense. And heart rate is pretty self-explanatory. It's the number of times the heart beats per minute. So it makes sense why the cardiac output unit is volume over unit time. All right. What affects cardiac output? What causes it to increase or decrease? So we know from our basic math that for some part of the equation to decrease or increase, these variables have to change. So really, we're going to be looking at how stroke volume and heart rate change to modify cardiac output. So heart rate is affected by these effects called conotropic effects. And conotropic effects are, the main conotropic effects are via the parasympathetic nervous system and the sympathetic nervous system. So the parasympathetic nervous system activates these receptors called M2 receptors, which result in the decrease of heart rate. And the sympathetic nervous system activates these receptors called beta 1 receptors, which result in an increase of heart rate. So if you increase this, this will increase. If you decrease it, it will decrease. Makes sense. Stroke volume is a bit more complicated. It's got, not complicated, but it's got a bit more to it. So, stroke volume is affected by three main variables. You have contractility, afterload, and preload. Let's start with contractility because the easiest one. Contractility is just the ability of the ventricles to contract, and it's also called inotropy. And it's affected by inotropic effects. And the main inotropic effects, kind of similar to the conotropic effects, are from the sympathetic nervous system and the parasympathetic nervous system. The sympathetic nervous system activates the beta 1 receptors and causes increased contractility of the ventricles and the atria. The parasympathetic nervous system, on the other hand, activates M2 receptors and only causes a decrease in contractility of the atria. Okay. And obviously, if you increase the contractility, if the ability of the heart to contract increases, then you would increase the stroke volume and the pressure that you generate. Moving on, we'll talk about afterload. Afterload is the amount of pressure the ventricles have to overcome prior to contraction. So we know in order to open that aortic valve during the cardiac cycle, the left ventricular pressure has to increase beyond the aortic pressure. So that pressure that the ventricles have to overcome, that's afterload. And it's approximated by mean arterial pressure, and that makes sense, as the mean arterial pressure would be equal to the pressure that's in the aorta. And if you increase afterload, if you increase that pressure needed to open that aortic valve, then you'd have a decrease in your stroke volume and an increase in pressure. And afterload is affected by three main things. Mean arterial pressure, which makes sense. We already talked about how afterload is essentially approximated by this variable. Vessel health and valve health. We'll talk about vessel health first. So, if you have atherosclerosis of the aorta, the aortic lumen essentially narrows, okay? So if you have that lumen of the aorta narrowing, then you have to push the blood into a smaller amount of space. And that smaller amount of space means more pressure. So essentially, you have to push the blood into a greater amount of pressure. So that would result in afterload increasing and the stroke volume decreasing. Same with valve health. If you have a stenosed aortic valve, a narrowed aortic valve, what would happen is that you have a smaller opening for the blood to flow out, therefore increased pressure and therefore increased afterload. Finally, we'll talk about preload. Preload, I like to understand it as the amount of blood in the ventricles prior to contraction. And you might see another definition as it's the amount of sarcomere stretch before the contraction, and it's essentially the same thing. Preload, it's also, and I'll explain later, obviously. So preload is also called end diastolic volume. And if you break that definition down, end diastolic volume. So that's the amount of blood after diastole is over that's in the ventricles. And if you have increased blood, you have more stretching of that ventricular chamber. And that leads to the sarcomeres in the cardiac myocytes to stretch more. And when they stretch more, that increases stroke volume. And now that is the Frank-Starling relationship. It states that increased sarcomere stretch leads to increased stroke volume, and therefore end diastolic volume, increasing that would increase the stroke volume until a certain part where it plateaus. All right. Finally, we'll talk about what affects preload. So preload is affected by atrial contractility, venous return, ventricular compliance, and valve health, particularly the mitral valve and the aortic valve. So we'll break these down individually and you'll see how they make sense. So if the atria can contract more, if they contract properly, then you'd have more blood entering the ventricle during diastole, which therefore increases preload. That makes sense. Venous return is the amount of blood that is returned to the atria. And if you increase the amount of blood that's returned to the atria, therefore the atria will put more blood into the ventricles. So therefore, that would cause an increased preload. Ventricular compliance, recall that ventricular compliance is the ability of the ventricle to stretch in response to volume changes. So if you have a ventricle that's compliant, that's able to accommodate more blood, that means the preload is increased. And finally, if you have a stenosed mitral valve, for example, you have less blood entering through the valve from the atria, and therefore you have preload decreased. On the other hand, if you have an regurgitant aortic valve, so blood from the aorta is going back into that left ventricle, you would increase the preload. And that is essentially cardiac output and the Frank-Starling mechanism. Thank you for watching, and let me know if you have any questions.